Welcome to qnawire.
Okay, this is problem number 4, chapter 23. For this problem, we are given the wavelength, lambda. It's going to be equal to 630 nanometers. So let's go ahead and convert that to meters. So to do that, it's 10 to the negative 9 meters for every 1 nanometer. So then this is going to be equal to 630 times 10 to the negative 9 meters. We are also given the length from the double slit to the screen, so that length is 1.2 meters. And we are also given the length from the 0th order bright fringe to the 3rd order bright fringe, so it's y sub 3. That one's going to be equal to 0.80 centimeters. So again, we're going to convert this to meters. So 10 to the negative 2 meters for every 1 centimeter. So we are converting to meters here before we start, just to ease calculations later. Okay, we are given the length from the double slit to the screen, and we're also given the distance from the 0th order bright fringe to the 3rd order bright fringe. So what we can determine from this is well, whether small angle approximations are valid. If they are valid, then we can use that information to determine the slit separation. So here in the double slit experiment, you usually have your double slit here, represented like so, and then you have a screen, a distance L away. So what we're given here is L, which is this red line, and then we're also given y sub 3. So that's going to be the distance from this first bright fringe, 0th order bright fringe to the 3rd bright fringe. We're given that distance, this vertical distance, and that is called y3. The angle here between this blue and red line, we can label that as theta sub 3. The vertical distance here is y3, and the horizontal distance is L. So from the geometry, we get tangent of theta 3 is going to be equal to y sub 3 over L. Let's go ahead and solve for theta 3. We take the arc tangent on both sides, and then we're going to plug in the individual values. So y sub 3, here it is in meters, and we also need the length, capital L, which is also in meters, so that's just 1.2 meters. Okay, let's plug this into our calculator and see what we get. We're going to get approximately what? Okay, we get approximately 0.38 degrees. So this is a angle less than 1, so it's a small angle, so small angle approximations are valid in this case. So to this 3rd order bright fringe here, we can use the other formula for the double slit experiment, which says that d sine of theta m is equal to m lambda for constructive interference point, which this 3rd order bright fringe is. So here we'll solve for sine of theta m. By dividing d on both sides. And this is sine of theta m. Okay, but for small angle approximations, this is going to be approximately equal to tangent of theta m. tangent of theta m, which we know it's going to be y sub m over L, right? You can generalize this 3 to any m here. So then we can set those two things equal to one another. So we could get rid of the trigonometric functions here, and we could just set m lambda over d is going to be approximately equal to ym over L. Again, this is only valid for small angle approximations. Here, this is satisfied because our theta 3 is 0.38 degrees. So we can solve this equation for d. Let's go ahead and do that. So what we can do first is multiply both sides by d. If we multiply both sides by d, actually let's multiply both sides by d and L, dl on both sides. So we're going to get m lambda L is going to be equal to dy sub m. Now let's go ahead and solve for d. D is going to be, we divide y sub m on both sides. Okay, this is valid for small angle when small angle approximations are valid. So here, let's go ahead, since we have y sub 3, and we have lambda and L, we could go ahead and solve for d here. So let's do that. D is going to be equal to m, which is 3 in this case, times lambda, which is this value here. So we're going to multiply 3 lambda. We need capital L, which is 1.2 meters. And we're going to divide this by y sub m, which in this case says m is 3. We're going to go ahead and divide that by this quantity here. When we plug this into the calculator, let's see what we get for d. We get approximately 2.8 times 10 to the negative 4 meters. Okay, so let's do a conversion to millimeters. So 1 millimeter is 10 to the negative 3 meters. So this goes to the numerator since it's negative, and then we're going to be left with 10 to the negative 1, so that pushes the decimal place to the left. So here we're left with 0.2828 millimeters, like so. So that is the slit separation. Okay, the final thing that we could determine is, since we're dealing with light, we know that c is going to be equal to lambda f, where c is the speed of light, equal to 3.0 times 10 to the 8 meters per second. Here we're going to solve for the frequency of this light. So f is going to be equal to c over lambda. So c is this quantity. And let's go ahead and divide by lambda. And when we put this into the calculator, we get approximately 4.8 times 10 to the 14. And then for our units, meters cancels with meters, we're left with seconds, inverse seconds, which is hertz. Okay, that completes the problem.